Hey everybody, and welcome to a video on the infamous Monty Hall problem. In this video, we're going to use Bayes' theorem to come up with a really simple solution to this problem. Alright, so first let's state what the problem is. You may have heard of this before. It's a fun brain teaser. Loosely based off of the famous game show Let's Make a Deal, which had a host named Monty Hall. So in the game, we're supposed that you're given three doors, right? Door number 1, door number 2, and door number 3. Now you're told that behind two of these doors are goats, and you don't really care much to receive a goat, but behind one of the doors is a brand new car, right? And that's the door that you want to get, right? So let's suppose, right, that you, we'll just fix this for concreteness. Let's suppose you randomly choose a door, you choose door number 1, right? Now initially, right, you think the probability that the car is behind any door is equally likely, right? So I'm going to let D1 be the proposition that the car is behind door 1. Door 1, right? And similarly, right, I'll let D2 mean, right, it's behind door 2, and D3 mean it's behind door 3. So what I'm saying here in this initial assumption is that, right, the probability of D1 is equal to the probability of D2 equal to the probability of D3, right? You're equally likely, each one is equally likely to be the one that has the car behind it, at least up front, right? Okay, now here's how the second stage of the game works. So the first stage, you pick your door. Second stage, Monty is going to open, Monty, who knows, by the way, what's behind each of the doors, is going to open up one of the doors you didn't pick. So in this case, either door 2 or door 3, right? And he's going to reveal a goat. So we know that at least one of the two doors, right, door 2 or door 3 has to have a goat behind it because only one of the doors has a car behind it. So he's going to be able to choose one of them and make it, and make sure that it's a goat door and open it up and reveal a goat to you, right? So in this case, right, you know, since you chose door number 1, you know he's either going to open door number 2 or he's going to open door number 3 and reveal a goat, right? So I'm going to choose letters to represent those propositions. So let's let O2 be the proposition that Monty opens door 2. Okay, and let's let O3 be the proposition that Monty opens door 3. All right. And so we know that he's going to do that. And then after he does that, right, you see the goat behind either door 2 or door 3, Monty is then going to offer you an option to switch your door, right? So you can either stick with your original choice, in this case door 1, and open it up and see what's behind it, and get whatever's behind it, or you could switch to whichever door is not opened at the second stage and get whatever's behind it, right? You'd have to forsake your original choice, though, in order to do that. So the question is, what should you do? Should you switch or should you not switch when Monty offers you the opportunity to do so? And it's clear that whether you should switch or not depends on the probabilities, right? Do you think it's more likely that the car is behind the door you originally chose, or is it more likely that the car is behind the door that Monty has left unopened and that you didn't choose, right? So that's what we have to try to figure out, which probability is greater, right? Now, it's intuitive to a lot of people that once Monty has opened a door, say he's opened door 2 and revealed that there's a goat behind there, it's intuitive to a lot of people that, oh, there's only 2 doors left, 1 and 3. The goat was equally likely to be behind either one, so it's probably 1/2 that it's behind the door I chose, probably 1/2 that's behind the other door, door 3 in this case. So there's no benefit to switching. I might as well stick with my original choice. The probabilities are equal. Right? That's an intuitive thought that a lot of people have. It turns out, right, we should be careful here, though, right, and check whether that's really right. And to check whether that's really right, we'll use Bayes' theorem, right, which we proved in the last video. So let's see, how would Bayes' theorem work here? Well, what we're interested in is the probability that our door, D1, has the car behind it, given that we learn that Monty opens, say, door number 2. Let's say that's what we learn. Right, what is this probability here? So we'll say he opens door number 2. What's our new probability for the car being behind door number 1? The intuitive answer that some people want to give initially is, oh, it's 1/2. But let's be more cautious. Let's work through Bayes' theorem here. So what does Bayes' theorem tells us? Well, it tells us this is the probability of him opening door number 2, given that I chose that it's given, excuse me, that the car is indeed behind door number 1, times the probability that car is behind door number 1, over, again, the same thing, probability of O2 given D1 times the probability of D1, plus the probability of O2 given the other possible hypotheses we could have. The other hypotheses are that the door is behind door number 2, or excuse me, the car is behind door number 2, and the car is behind door number 3. So O2 given D2 times probability of D2 plus probability of O3 given D3, excuse me, O2 given D3. We're keeping the evidence proposition the same there, so D3 times probability of D3. All right, and that's the whole thing, right? This is just an application of Bayes' theorem that we learned in the last video. All right, now let's see if we can figure out what each of these terms are. So we know the prior probability of D1, D2, and D3, those are all 1/3, right? Because it was initially 1/3 likely. Now, what's the probability that Monty would open door number 2 given that the car is really behind door number 1? Well, if the car is really behind door number 1, then Monty feels free to open either door 2 or door 3. So let's say he flips a coin in that case, right? There's a 50% chance he'll open door 2, 50% chance he'll open door 3. If that's the way it works, then there's only, right, a 1/2 probability that he would open door 2, given that the car is really behind door 1, right? All right. We'll divide all this by the same thing, right? 1/2 times 1/3, right? Plus, right? Now, what's the probability that Monty would open door number 2, given that the car is really behind door number 2? Well, that's 0, right? Because he would never open a door and reveal a car. So that's 0 times 1/3. Plus, what's the probability that he would open door number 2, given that the car is really behind door number 3? Well, given that all of this, right, in this whole setup here, I'm conditioning on that we've chosen door number 1, right? We know that we've done that. So in that case, right, he has to choose door number 2, given that the car is behind door number 3, right? So that would actually be probability 1, right? 1 times the prior probability that the car would have been behind door number 3. It's 1/3. Right? All right. So now, if we go through this, we can cancel out the 1/3, right? And we're left with 1/2 over 1/2 plus 1, which is 3/2, which is equal to 1/3. So this is now interesting. We didn't get 1/2 as an answer. We got that the probability that the car is behind door number 1, given Monty opened door number 2, is still the same as it was before. It's still 1/3, which means the probability of the competing hypothesis, which at this point is now that the car is behind door number 3, right? That must be 2/3, since the two of them together have to add up to 1. So it's actually more likely now that Monty's opened door number 2. I should judge it more likely that the car is behind door number 3 than that the car is behind door number 1. So I should switch my choice, right? This is just a simple application of Bayes' theorem, and yet it yields this sort of counterintuitive result. So this shows you how strange probabilities can be and how important it is to work through things very carefully. Now, we note that we would have gotten the same answer right if we considered learning, instead of learning that Monty had opened door number 2, if we learned that Monty had opened door number 3, by the exact same sort of reasoning, we would have gotten the same conclusion that the agent should switch. You can maybe gain some intuition for why this result is plausible if you think that right at the start of the problem, there's a 1/3 chance that you have things right and that the car is behind your door number 1, and 2/3 chance that it's behind either door 2 or door 3, right? So initially you think it's more likely that you didn't get things right, that the car is not behind door number 1, that it's behind either door 2 or door 3. And there's a sense in which you don't really learn much when Monty opens either door 2 or door 3, or at least you don't learn anything that's relevant to shifting the relative probability of the car being behind door 1 versus the car being behind door 2 or door 3, right? You already know that one of the two doors, door 2 or door 3, has a goat behind it. And you know that Monty's going to open a door with a goat behind it, right? So you shouldn't be too surprised when he does, right? And shouldn't be as inclined to shift your choice. Another nice way to gain some intuition for why this is not totally crazy is if you consider a many-doored version of the Monty Hall problem. Suppose that rather than having just 3 doors, we have, let's say, maybe 100 doors, right? 1, 2, 3, 4, 98, 99, 100, right? And suppose that again, Monty's going to let us pick a door. Maybe I'll pick door 1 again, right? And then Monty knows exactly where the car is, right? Let's say 99 of these doors have goats behind them. One of them has a car behind them, right? It's very unlikely you got lucky and picked the door that had the car behind it. It's only 1% chance, right? So let's say that, right, you think it's very likely that the car is somewhere else, right, out here. Maybe this is where the car is, behind door number 4. So Monty, right, is going to go through all the other doors and open all of the other doors, right? He's going to open up 98 of the other doors. There's 99 other doors besides for your initial door. He's going to open up 98 of them that he knows have goats behind them. And we know that there have to be at least 98 of those cars that have goats behind them, right? And let's say he does that, right? He opens them, opens, right? There's 2 things that could be going on with the door that he doesn't open, door 4, right? Either, right, you actually, right, the car is actually behind your door, and it was just, by chance the door 4 was the door that Monty decided not to open, right? But that's very unlikely, right? That had very low prior probability. It was unlikely that you had gotten the door 1, right, right from the start, right? That you would pick the door that really had the car behind it, right? The other possibility that could be going on that's more likely is that, right, you didn't get it right, and Monty, right, just intentionally selected out door 4, right, didn't open that one because he couldn't, because it was the door that had the car behind it, right? So in this case, right, at least for a lot of people, it seems much more intuitive that, okay, yes, we should switch our choice, right? If this sort of thing happens, I'm going to want to switch to door 4 rather than my original choice of door 1, right? But the exact same sort of thing is going on in the original Monty Hall problem, just with much smaller numbers. Right? So perhaps that gives some intuition for it. But the real thing we want to focus on is the importance of Bayes' theorem and working through these things carefully. All right. Thanks for watching this video. Please complete the participation poll, and I'll see you next week, guys.